Good afternoon. Thanks for listening, and it's a great honor to stand here for sharing. My name is Xinghao Tang, a security researcher from gemu-kvm. In last May, since the rush of women vulnerability, large numbers of public cloud vendors have been deeply affected. After systematic analysis, I was interested in the vulnerability and was wondering that if this kind of vulnerability can be found in numbers at one time. So I started my research. After 4 months research, I completed a semi-automatic fuzzing framework with which I could realize a vulnerability discovery of hardware virtualization components in multiple kinds of virtualization systems. My team had found a significant quantity of serious vulnerability by means of this fuzzing framework in gemu and VMware workstation. Before start sharing, let me introduce my team. gemu-kvm. My team is the first professional cloud computing and virtualization security team in China. My team focused on researching about the techniques of attack and defense in mainstream virtualization systems. Recently, we have gained significant achievements in virtualization, fuzzing framework, guest machine escape technology, and Hypervisor vulnerabilities defense product. Okay, today I would like to share the following research achievements with you guys. The theoretical foundation and the details of virtualization system fuzzing framework is running precisely and key problems were faced and how we solved them at last. Later, I will also show 2 cases which contains more details of the device emulator vulnerability discovery technology. At the beginning, let's talk about the virtualization system and its brand new attack surface. Virtualization technique plays a vital role in realizing cloud computing conception. It can allocate physical resources dynamically and flexibly. The main virtualization system includes gemu-kvm and VMware. The VMware product series are mostly used in the private cloud environment because of its strengths in product maturity, while Zen and kvm products are popular in the public cloud solutions. We could see that virtualization products are still in procedure of development. There are many two development trains: nested virtualization and tiny Hypervisor. However, it's really hard to say which one or if both two trains can turn to many directions. It may need more time to reach the conclusion. Servers applied with virtualization and technology are completely different from common servers. One or more virtual machines can operate in the virtualization servers. Additionally, all these virtual machines can work independently. Most of functions provided by physical devices, which are necessary in virtual machine operation, such as the CPU, MMU, adapters, and keyboards, they are provided in virtualization system as software services. Part or even all the physical hardware functions can be virtualized. We can see that it's really amazing and advanced. However, maybe we are facing big security risks when we do this. Before this revolution of cloud computing, hackers always attack the physical servers. However, recently, hackers would rather directly attack the virtualization system. They slip into the guest machine and launch attack to server and the core network. We call this kind of attack as a virtual machine escape. The virtual machine escape is the most dangerous and brand new attack in cloud computing environment. There are 3 steps for launching virtual machine escape attack. Firstly, entering the virtual machine escape environment by renting the cloud servers or through the web tab. Then make sure the type and version of the virtualization system by collecting information. Finally, complete the attack by utilizing vulnerability exploit tool. Then can control the host machine. We can clearly see that hackers heavily rely on vulnerabilities during process of launching the get machine escape attack. So whether or not there contain big amount of vulnerabilities in virtualization system, after analysis, I believe that hardware virtual components or the device emulator can be used as an attack surface. And why we say that the hardware virtualization device in the is an attack surface worthy of concern. Firstly, there are different kinds of hardware virtualization components. For example, there are more than 30 within gemu and more than 20 within the VMware. Second, the hardware virtualization components bridges between the get machine and the host machine. The third, we could add malicious code inside of those components' memory, then execute the code. This will lead to really dangerous vulnerabilities. However, we need to note that the danger of hardware virtualization components vulnerabilities is limited. Memory permission in host will determine the effects of vulnerability exploitation. If the permission not enough, not many exploitation operations can be deployed, then we may need permission escalation by other vulnerabilities. As mentioned above, heavily used cloud computing hardly can be seen as secure. Compared to traditional IT frameworks, virtualization escape is a new kind of attack surface. According to this attack surface, I designed a set of semi-automatic fuzzing framework, which realized about discovering vulnerabilities in virtualization system. And I will start my discussion in the following part about the operation principles and the implementation details of this fuzzing framework. As a task protect for virtualization system, the attack surface we focus on is the hardware virtual components, or we call it the device emulator. We have finished testing works for several components within gemu and the VMware workstation, and we found 20 vulnerabilities, security vulnerabilities. The biggest challenge we faced is that it's hard to test the target components of a bottom layer. And we could see that this testing project will focus on testing more kinds of virtualization systems in the future, such as Hypervisor. We will also add more attack surfaces fuzzing functions. Before proceeding further, let me walk through the differences between vulnerabilities discovered in hardware components and the traditional targets. Let me make a comparison to explain it. The normal vulnerability discovery aims at the user level software such as IE, Flash, and Nginx, or drivers components in kernel space. Well, virtualization vulnerabilities fuzzing mostly targets at the basic components with physical device functions, like the network card emulators, keyboard emulators, and so on. And secondly, testing way seems more particular in virtualization fuzzing framework. For instance, in normal fuzzing framework, web page can be used for IE fuzzing. Remote network packet can be used for the NGX server fuzzing. IO control function can be used for the driver modules fuzzing. However, we can't even use any one of these data in the device emulator components fuzzing. So what's the best way for testing the device emulator components? At first, it's necessary to analyze the data which follow to the component and its processes of generating and transfer. Second, sending out the testing data to target modules. According to the device, which could be tested through gas machine data flow, we have two ways to construct testing data. The detailed processes are one way to alter the contents and the order of data transmitted between driver components in kernel space at a system runtime. And another way is to modify the initial data values of those components while the system is starting. And about the device which can not be tested directly, testing data must be determined and limited by modules from more than one layer at first. The third, recording all of tiny abnormal activities via hardware virtualization components are dealing with testing data. Fourth, in view of those abnormal activities, finding out the traces that cause the issues, and optimize fuzzing framework. When we started working on this testing framework, we have already considered about its flexibility and compatibility. For example, utilizing modular way to realize several functions like the testing, monitoring, and analyzing. And we also make sure our testing framework could run in multiple virtualization systems like Virtualization, gemu-kvm, and gemu-kvm. During the development processes, we use Linux as a guest machine operating system. We use Python to realize data transmission between the three parts and to manage guest machine operation. We use C language to implement Linux Java components in guest machine, and we use XML as the storage from R for test data using unit storage. While enhancing the compatibility, we want to make sure data unification between fuzzing framework and the testing data of the specific target. Therefore, we need to optimize our fuzzing framework according to different targets. This will need us to consider language we use, development environment, even the coding style while developing hardware virtualization components. For instance, for VMware software, developers pay more attention to extreme conditions, so we need to bypass them. And when abnormal situation occurs, the main method for exception handling is directly exists software. According to gemu, last three conditions are present in its devices, and coding styles are very similar. As shown in figure, you could clearly see that each component and their data flows. We divided the framework into 3 parts: the host machine, virtual machine, and the controlling center. And the 3 components are running in every part: monitor, clean, and the server. There are many packs of modules in each component. The first server, which is installed in controlling center. Server contains data testing module and the data communication module, monitor log storage module, and the cleaned storage module. Second, cleaned is installed in the virtual machine. The clean contains device emulator, analyze module, system hook module, and the testing data load module. The third, monitor is installed in host machine. A monitor contains a Hypervisor instrument module, data communication module, and the monitor log record module. And these modules will work as a follow sequence. At the beginning, setting up network and hardware environment, launching server, clean, and monitor. After that, clean will allow system hook module get all of devices, emulators, basic information. Then clean will ask servers to testing data of emulators. Server will send out required data. The cleaned, resolved, and the load testing data then launch the test. And at the same time, monitor will continually monitor how the hypervisor working and record down the logs. After the above steps, testing for clean finish and will notify the server. Server will get logs from clean and monitor save it. Then server will launch log analyze module, determine if anything wrong happened, and notify. That means security researcher will analyze program exceptions and optimize the fuzzing framework. And let's talk about the server. Server programs are running in controlling center server. These programs control the whole testing process and collect data of every about steps. This program works semi-automatically. Security engineer duty are analyze testing results and optimizing the testing data modules. Here are some noteworthy function points. The first one is that some vulnerability will cause crashes of host machines. Therefore, we need to pay more attention to timeouts happened in host machine. So the second one is recovering the testing environment of virtual machine. The last one is maintaining the testing data and the related logs in Pi. The clean programming is running in virtual machine. One main function of this program is to get hardware virtualization device emulators information. The operation principle of clean is emulating the device manager of Windows and index related information of hardware virtualization components, including device name, accessible memory, and the ports. All this information are determined by the drive module while guest machine operation system starting. And in the Linux system, this information are stored in files. We could view them by LSPCI commands. However, there are several levels of hardware virtual device emulators. We could only see the top layer in the device manager. A client program will use testing data from controlling center. Testing data contains the access entry of the target commands, received data structure, and the restriction set from this component to field of data structure. In the first part, the target components received info, which are virtual signed to through L ports or L memory. In the second part, different target component fit different data structure, and later I will analyze two kinds of network card, which are E1000 and PC9. It's clear to see that for different network card, their data structures are different. In the third part, same kind of hardware virtual components plays similar roles in different virtual systems. Meanwhile, field restrictions of data structures in VMware and QEMU are different. We need to define two sets of limited ranges for related field. Sending out testing data to target components is a relatively simple process. The first step is that user layer of client generators testing data sends the request to client kernel according to specified operation from data. The second step is that client kernel applying for memory according to the request, fills out memory and sending out memory information to specified ports. And we can say the main functions of client program are getting target components, generating testing data, sending test data. Additionally, send the logs to server of controlling center in time. And let's move to monitor in hosting machine. A monitor program will realize functions as follows. First one, managing virtual machines like snapshot management, power management of guest machine, features management of virtual machine. The second one, dynamically debugging the running process of guest machine, such as debugging of launching guest machine, loading, and the debugging scripts record debugging info. The third one, keeping record of guest machines running process, including recording running process of user layer and the driver module and of kernel space. There are other things monitor will do here. When testing QEMU, we must set up guest machine hardware devices by modifying software parameters. We can modify QEMU's source code for recording the process. When testing Virtualization, we can also manage virtual machine hardware device by modifying the configuration fields. The debugging method is that use WinDebug to load main process of VMware, then load the WinDebug debugging script for recording running process of the virtual machine. Test symbols will cause three responses: guest machine operation, system crash, virtualization system crash, and the invisible results. Guest machine operation system crash happens when there are flaws in driver modules because of the system adaptation issue. This won't help us a lot. And we should pay more attention to get the machine crash and invisible results. Usually we will find vulnerabilities by analyzing them. For the get the machine system crash, it's more obvious to be detected. It's often caused by several vulnerabilities which are triggering the virtualization system, such as heap overflow, double free, user free, and so on. The invisible results only can be recorded by analyzing get system logs. In the monitor program, we need to use advanced debugging skills to help security engineers to find new security issues. Automatically record details of virtual machine running, especially changes of key values. That's really necessary. Based on the record, we can estimate the whether there exists information leakage or other logic vulnerabilities or some other vulnerabilities. The instrumentation technique vary based on if there exists symbolic info or source code in the system we test. As for software without source code or symbolic information, like Vim Workstation, we adopt another method to implement instrumentation. At first, we reverse the software information, look at the key code and variables, then we insert backpoint to critical points when writing the debug plugins. At the beginning, when we use this filing framework, we get many crashes in short time. However, after digging out relatively simple vulnerabilities, how we gonna find with more complex issues? At that time, we saw that maybe we need to optimize the filing framework. Because our method of virtualization vulnerabilities coverage by fuzzing heavily rely on the accuracy and diversity of testing symbols. And in most cases, accuracy and diversity of symbols contradict with each other. So we may need massive symbols and testing results in detail to optimize testing data generation. Especially the coverage area of technical recorded in monitor logs. This testing record can help us optimize testing data. By analyzing client logs, we could decrease invalid combination during testing data generation. By analyzing server logs, scanning, and analyzing testing parameters and the crash parameters of data template. And during the process of developing and using this filing framework, we found more than 20 security vulnerabilities. Here the CVE IDs for those vulnerabilities which are public. So I'm confident that our filing framework are now working efficiently in discovering hardware virtualization component vulnerabilities. Recently, we have found several more attack surfaces in virtualization products. We believe that this framework will help us to find more vulnerabilities in the future. And I will show you two cases about the device emulator working and vulnerabilities within them. These two components realize the functions of network card. Like I mentioned before, data packet in guest machine get into the host machine. The access internet through host physical network card by helping with the network card emulator. Let's pay attention to the operation principles of gigabit network card emulators. In the first place, operation system selects corresponding driver according to the type of network card when it starts. Then driver will distribute outputs, memory address, initialize the device status, and allocate memory resources for descriptor table. After the operation system started, while the data is being sent, network packet will enter into the device driver component. Afterward, device driver components will insert data into the descriptor table and assign TDT register of network card to be true. And when the gigabit network card detects that TDT register has been reset, then it will process the descriptor table. There are three types of descriptor in the descriptor table: context descriptor, date descriptor, and legacy descriptor. According to the descriptor location and content, the gigabit network card will abstract the network card, network packet info, and send it to the virtual device adapter. After which, the TDT register will be set false. After that, whole data packet transmission process finished. There are 2 points we need to pay attention to here. The first one is that the descriptor table is of the ring-like memory. When data size exceeds the length of the descriptor table, it will be overwritten from the beginning of the descriptor table. Due to this reason, the buffer overflow vulnerability will not occur. The second point is that gigabit network card use TCP segmentation offload technique to improve passing rate of network packet. Due to this complicated logic, there exist vulnerabilities in the source code of network card emulator, which is related to this technique. And while testing the gigabit network card emulator of QEMU and the VMware workstation, we found 2 vulnerabilities by means of this work. And these 2 vulnerabilities are in similar principles. And we are able to control the kernel components of guest machines operating system. Hijacking of cloud flow is possible, and setting several variables of code. The second component is PCNet network card emulator. Although the way that PCNet deal with descriptor are totally different from E1000, or we call it the gigabit network card, but they are doing the similar things, like dealing with data packet info, then set this info to bottom layer adapter for further steps. Internal process follow of PCNet shown as in this figure. By means of writing output PCNet components, capture the operation of writing control and status register. Then it will get into the function we wrote for dealing with the data transfer. Then the components will separately get into processing of sending and receiving data packet. During the whole process, interesting detail is that adding CLC after the data packet. we found one vulnerability inside the code for PCNet dealing with the received data packet. Attackers could cause the buffer overflow in constructing descriptor. And what's exciting is that we could overflow the constructed data to function points. This will make launching guest machine scale attack possible. Next, I would like to play a demo video about guest machine escape from KVM the gemu environment. This video shows another speech topic of our team. Due to some reason, the author didn't show up here for speech. In this video, hackers execute the vulnerabilities, exploit coder at first, open a remote shell of host machine. Then hacker connects the shell from another machine, performs malicious activities. And about more details inside this, in this video, please contact my colleague by email. This email. And today I discussed about the virtualization system fuzzing framework using by my team, and we will continue to working on this framework to make it more efficient and accurate. I hope my speech could bring more thoughts. And please stay tuned for our more achievements in virtualization systems creative field. Thanks for patiently listening, and welcome to contact me through the above email. Okay, thanks. Any question?
I'm curious whether you've thought at all about the mitigations in Qubes OS as a way of effectively avoiding some of these issues.
Slow, please.
So, Qubes OS is an operating system which tries to simplify some of the communications between VMs to effectively have less access to devices, things like that. Have you looked at that at all, what they're doing?
I don't get.
No problem.
Maybe you can send email to me. Okay.